Hi everyone, welcome back to the channel. In today's video, we'll discuss a very interesting topic uh, in microwave and especially in antennas and arrays. So the topic is called a Rotman lens or Rotman-Turner lens. It's very popular and it's becoming more popular today, nowadays, I guess. So that's a good time to maybe discuss the theory and design equations behind this. Okay, so we'll discuss, say, I'll call it intuition, or let's say introduction rather. So it's introduction and maybe theory instead of design. Okay, so in this video, we'll discuss the theory behind it, like the equations, we'll derive the equations for the Rotman lens. And in the next video, we will look at simulations. So we'll simulate it in HFSS. We'll take the equations that we'll have developed today, and then we'll actually make a 3D model, simulate in HFSS, and look at the beam steering. Okay, so what is a Rotman lens, right? Let's start something simple with something simple. So Rotman lens in general can be, so if I have, let's say, a black box, and coming out of this are many antennas, like an array, right? And what I want to do is I want to steer this beam, the beam of this array, in different directions. So let's say I want to steer it in this direction, then maybe in this direction, and then let's say in that direction. Different color. Also like this and like this, right? So there are many ways to do this. One way is to use a phased array, but a sort of simpler approach, which is totally passive, is to use something called a beam forming network. Beam forming network, or BFN for short. And what that is that it's a set of inputs and outputs. So I have, let's say in this case, I want 5 discrete beams. Then I would have 5 inputs. So let's say I have 1, 2, 3, 4, 5. And what I want is if I put a signal into this port at the input, then I get this beam. If I use, let's say, this port, then I get this beam. If I use this port, I get this beam, and so on, right? What else did we use? We used purple, which would be this port goes there, and green, right? So this port goes here. So depending on which port you excite, you get a beam in a specific direction, and there are obviously a discrete number of ports on the left. So you get a discrete number of beams, right? So that's a very useful thing to have. And these kind of networks are called beamforming networks. So the Rotman lens, in fact, is a beamforming network. It's one way to do this. And there are other ways, like a Butler matrix and so on, but we won't be discussing those today. So today we'll talk about something specific. That's the Rotman lens, which is a beamforming network. Yeah, it's essentially a microwave version of a lens design, and we'll see why that is. Okay, so why use this rather than other beamforming networks? There are several advantages. One is that the most important one is that it's wideband. Okay, because it relies on what's known as true time delay. And we'll see what that is. But essentially, it doesn't use any specific frequency dependent phase shifters in the sense that any lambda or 4 lines or any phase shifters that are fixed with respect to frequency. Right, so it relies on actual true time delay, and we'll see what that is, and that's why it becomes very wideband. It's very important. Okay, and the next thing is that it's also wide angle, so you can generate wide angle beams. That's useful. And of course, it's low profile, since it's just, and we'll see actually it can be made along PCB and easy to fabricate, even up to high frequencies. So that's why it's sort of popular, I would say. And if you look at the applications, there are many applications for it. Right, so Of course, it can be used for radar, right? Where you can scan stuff. You can scan a scene or do angle of arrival estimation. For example, in automotive radar, sometimes it's used. Can be used in communications, also very important, right? Because it's ultra wideband, so you can use it in ultra wideband communications, 5G, 6G, and so on. Also use beamforming networks, so it's very useful there. And more recently, it's also been used in, it can be used for RFID, right? And IoT applications, right? Like some people, I mean, in recent years, people have also proposed it for wireless power transfer. So this is actually sort of becoming very popular now. Wireless power transfer. You can look at work done by Ali Need and Manus from Georgia Tech if you're interested in this specific application. Okay, so these are the various applications and advantages of a Rotman lens. Okay, if you actually look at it, an actual Rotman lens, the image, it looks kind of strange, right? It has, all these kind of spokes coming out like that. And then maybe you have something up there, something down here, and then something coming out here. And then these guys go out to your antennas, and then these guys go to your inputs, right? So it looks kind of like a very funky design. But today we'll actually see why it's like this, what these ports are, what they're doing, right? And we'll derive the geometrical equations, we'll derive them from scratch, all the equations that define what this structure actually is, right? So, without further delay, let's get started on the derivation. Maybe before the derivation, we'll quickly go through a quick section on maybe the intuition behind what exactly this is, right? Why it came about. So I'll call this intuition. I like to focus on intuition. I think that's very important. Okay. So if you look at a typical lens, so let's go to optics now and say I have, a thin lens like this, right? Something like this. And something like that. If I place, let's say this lens has a focus, F, right? If I place, let's say, an antenna over here, let's say I place an antenna like that, then all the rays coming out of this, we know that once they go through this lens, they become parallel, right? On the other side. And that's kind of what you want, right? You want a beam, a narrow beam. If you look at the rays for a narrow beam, they should all be parallel. And that's very nice. But if I, in school, high school, I guess, you learned that, okay, if I'm up here, then what happens? Then the rays get parallel in this direction, right? Supposedly. Something like that. Right? I mean, these don't look very parallel, but in reality, they should all be parallel, right? And that is not entirely true, actually. So in reality, when you move off axis, you get something called chromatic aberration. Okay, in short, it's called coma. Right? And that's because, I mean, if you actually go through and write the geometrical optics equation for each ray, you'll see that they don't add up or they don't become parallel once they leave the lens. Or if you have parallel rays coming in from here, let's say you have parallel rays coming in like this, right? They don't all add up at this one point here. And you can look up this chromatic aberration if you like, right? So that's generally the case for a typical lens, right? And that's not good, right? Because you want to make a beamforming network. Let's say I have many antennas here. As I move away from the center position, the beam becomes broader and broader, right? So the beams that go this way are sort of become broader and you get some side lobes. And when you go this way, it becomes even worse, right? So the basic idea behind a Rotman lens is to fix this problem, to see if you can kind of correct for this coma aberration, okay, by doing something. Let's see what that is. Okay, so the idea is this. let's say I have the same lens again. Something like this. Focus here, right? And I have a set of antennas here. Okay. So now when I have a ray that goes out like this, let's say it hits this antenna. The ray goes here, hits that. And then you have this one that goes straight this way. So we know that these are all kind of parallel, right? When they come out, they should all be in phase. And that's well and good. That's what we had up there as well. But the idea behind a Rotman lens is that if I add a second parameter that I can control, let's say I can control the length of this line. Let's say I can meander it, right? So let's say from here to here, I can meander this line and add some extra length, some arbitrary length, right? To each of these sections. Then I have a second parameter to control, right? So then I can kind of control, let's call this W, which is the length of that line. And I can control this lens, epsilon, right? Then with this extra degree of freedom, can I have a second focus such that if I have some point up here, then when I excite from here, when I excite here, all of these are in phase. And when I excite here, I get a phase gradient, right? So that's the idea, is that if I add a second degree of freedom, a second degree of freedom using some extra lines here, right? Some arbitrary lengths. Then can I create a second ideal focus? So I have one ideal focus here. Focus number one. And I would like a second ideal focus here, out here, number two, right? Essentially what I'm saying is that, can I find a second point where this chromatic or chroma aberration doesn't exist, right? By adding a second degree of freedom. And we'll see how to do that, right? And of course, if I make these lengths symmetric, which means that, let's say if I make this length equal to this length, and then this one equal to this one, right? Something like this. And then this one is sort of straight. It doesn't matter, actually, this can be anything. But if it's symmetric in Y, then of course I also get from symmetry a third focus, right? Which is just the mirror image of this one. So these two would become mirror images, and you get essentially a third focus. Okay. So that's the basic idea, is that if I add a second degree of freedom with these, with some length of wires, maybe some lengths of wires out here, then can I correct for some of that chromatic aberration that I was seeing at a single point, which is away from our ideal focus that we started with? And the answer to that is yes, you can do that. And that's what the Rotman lens actually does. And we'll see how to do that. Okay, so let me just quickly recap. Basic idea is that adding W, which is an arbitrary parameter, gives an extra degree of freedom such that we can form a second, in brackets, and third ideal focus of axis, right? So that's the basic idea. Okay. Let's go ahead and see how to do that. So I'll actually go to the next page. And let's get into the lens design. and it's design. Okay. So there are some papers on this already. Although there is, as far as I can tell, there is no paper that derives specifically all the relations from scratch. There is a reference to a paper in one of the papers that I'll reference in this video, but I could not find that because that's like an internal document. So anyway, but the derivation is fairly straightforward and I was able to do it myself. So that's what I'll present here. And hopefully that's interesting. Okay, so let's get into some geometry and algebra. So it's all geometrical optics, which is just ray tracing. Okay, so let's do that. Okay, so what do we need? We have some axis, right? And then we have, let's say our antenna elements are out here. Okay, so I'll say, okay, some point here has my one antenna. So I have some other antenna here, and there are also some antennas in the middle, right? I have my ideal focus, which I'll call F1. And then I have two other foci, right, which I want to create. Call them F2 and F3. Okay, and then I have some kind of contour, something like that, which defines my lens. So I have one on that side and then one on this side. Maybe something like this. Okay. So this is essentially the lens, this whole thing. So it would look something like this, right? But I'm only drawing part of it. Okay. And let's label some of these lines now. So I have, let's say, some arbitrary point on this contour. I'll call it P of X comma Y, capital X comma capital Y, X comma Y. And my origin is on the right, on the left here, with X going that way and Y going this way. Okay, and then we'll draw some lines basically with geometry. So I'll call this line L2 from F2 to P. And then obviously this one would be L1. This one would be L3. And then the line going from here to here, which is this one, would be F1. That's the length of that. I'll label this point as O1. Let's call this one O2. And then I have some wire of length W. And let's call this one length W naught. Okay. Okay, that's good. And then let's say I have some normal here, some normal there. And I'll also label one more line, which is very important, which is this one. And I'll call this, I'll say this one has a length of F2. Okay, so that's basically the geometry. So W here is our sort of our second degree of freedom. And of course, you have F1 and F2, which are also degrees of freedom, right? Which you can set. Okay, so what do we want? We want that if we have a signal coming in here, then the trajectory from here to this point, from here going out like this, going through this to this point, and then of course, if you had something down here going to this point, they should all have the same length so that when you're out here, you should be at the same phase, right, to all of these points. And of course, if P is arbitrary, and let me actually label this length. Label inside. This length is Y3. So here P and Y3 are arbitrary. So y3 can be anything. It can be positive or negative. So it basically covers all of these points. Okay, and then P covers all of the points on this contour. Okay, so if you excite here, you need to make sure that the phase of all these elements is in phase. If you excite here, you want a phase gradient that's like this, right? So that all the rays coming out like this are in phase. And if you excite here, you want a phase gradient that is like this, right? So that all the rays coming out are in phase in this direction, right? So let's say that, if I want to go in this direction, let's say, so that is if I'm exciting at F2, then I want, if I'm exciting at F2, then I want the exit angle to be psi, right? Then, let's say this is a right angle. Then this length here is nothing but y3 sine of psi, right? Okay, good. So now we can write some equations. So based on this geometrical optics, if we want these three conditions to be met, which is that if I excite here, then they should be in phase. Here, one kind of phase gradient, and this the other kind of phase gradient. From that, we can write some equations out. Right, so let's write them out. So if I want, let's say I'm exciting F2, okay, and I want that phase gradient, which is y3 sine psi, right? Then I know that these conditions have to be met, right? I need L2 plus W plus y3 sine of psi should be equal to F2 plus W naught. Essentially, I'm saying that this length up to here, from here to here, should be equal to this length, right? And since this point and this point are arbitrary, I'm saying that for any point on this and a corresponding point on this, that length should be equal to the path length that comes to the central element. And that's the way you do phase beam steering, right? So that's one equation. And then, of course, you can write a similar equation for F3. So if I excite at F3, then I want L3 plus W minus Y3 sine psi is equal to F2 plus W naught, right? Of course, it's minus because now you want this ray to go up that way, which means you need to go back and then make sorry, which means you want the phase gradient to be, so in this case, the phase gradient was like this, right? So now we want the phase gradient to be like this. So this is the minus y3 sine psi, right? Or you could say this, or this, either of them. And that's why you need the negative part there. And then the last equation, of course, is just when you excite at the center, and then you want L1. Let me just scroll up a bit. And L1 is, of course, you want this length now only up to here to be equal to this length, right? So L1 plus W is equal to F1 plus W naught. Okay, so this gives us three equations, which are well and good. I'll call them equation set number 1. Okay, now what we'll do is we'll use some more geometry to develop 3 more equations so that we can actually use all of these equations to solve for these for the P of x comma y and the W's. So let me copy this, make a copy here, paste, let's make this smaller. Okay. Okay, so now what we can do is we can kind of erase a bunch of this stuff. Okay. What I will do now is I'm going to draw some more lines basically. Draw a vertical line up from here, something like that. And then a horizontal line from here. Okay. And then another vertical line down from here. Okay. I'll label a few of these. So I'll call this length as U and this length as V. And I'll call this as X prime. Okay. And of course, this is X and this whole thing is Y, right? Okay. So then I can write F2. Remember that this is F2, right? So this is F2. And I also want to label this angle. Call this angle as alpha. Okay. So now it's fairly straightforward to see that F2 cosine alpha is U plus X prime. F2 sine alpha is V minus Y, right? Y minus V, sorry. Y minus V, right? And note that L2 square is U square plus V square, right? So I can use the equations just above this. So basically I can substitute the value of U and V from these two in here. And that'll give me F2 square plus X prime square plus Y square minus 2 F2 this should be capital X and Y, sorry. X prime square plus Y square. And these should also be capital X and Y. X prime Y. Okay. F2 square plus X prime square plus Y square minus 2 F2 X prime cosine alpha minus 2 F2Y sine alpha. Okay, so let's rewrite that. L2 square, maybe I'll use black ink. L2 square is equal to F2 square plus X prime square plus Y square minus 2 F2 X prime cosine alpha minus 2 F2 Y sine alpha. And you can do the same thing for L3 square. It's the same thing, basically. Similar geometry will just give you, I mean, it's fairly straightforward. So I'm just going to write the final equation. X prime square plus Y square. I mean, it's the same thing as replacing Y with minus Y, essentially, right? Plus 2 F2Y sin alpha. And L3 can also be written very simply. Sorry, L1, because L1 is nothing but this square plus this square, which is F1 minus X square plus Y square, right? So L1 square is 1 minus X prime square. Sorry, not X prime. Yeah, x prime, which is the same thing as like f1 minus x prime is x, right? Square plus y square, right? So I'll call these equations as equation set number 2. Okay, so if you go back and actually revisit the first set of equations, you have L1, L2, L3 as something. And even the second set of equations gives you L1, L2, L3 as something. Right? So you just equate the two left-hand side and right-hand side of, or the right-hand sides of L1, L2, L3 squared from the first set of equations and the second set of equations. And that gives you a set of algebraic equation, set of three equations in terms of x, y, and w. So let me actually quickly write that because it's long and then I'll come back. Okay, so from 1 and 2, you get these three the set of these three equations. So that's your equation number 1, this is 2, and this is 3. And to simplify them, we'll make a few substitutions, which will help us along the way. So I'm going to make the following substitutions. I'll say small x prime is capital X prime divided by f1. So I'm normalizing everything to f1 now. Y is y over f1. And then W is W minus W naught over F1. Beta is F2 over F1. Gamma is sine psi over sine alpha. So psi was the output, the exit angle, and alpha was the angle of the focus with respect to the axis, right? If you go back to this picture. So this is alpha, right? And this is psi. And when they're equal, it means that, when you come in from here, you exit at the same angle. Right? If they're not equal, then you come in from here and you get a slight change in the angle when you go out. Okay, that's fine. Then zeta is y3 gamma over f1, which is the same thing as y3 sine of psi divided by f1 sine of alpha. And of course, just keep in mind that x is nothing but 1 minus x prime, since capital X minus f1 was equal to minus x prime. Right? F1 was x plus x prime. Okay. So with these substitutions, I'm going to rewrite these three equations again. And let me do that and come back. Again, it will take a few seconds. So, okay, so here are the three equations. So essentially, these equations we want to solve for x, y, and w as a function of the other parameters, right? As a function of y3, for example, and f1, f2, and so on. Right? So that's fairly simple algebra, really, is that you have three equations and three unknowns, and you can quickly solve it. And I'll actually show you how to do that. It's very straightforward, really. It's not that hard. So if I call this, let's say, equation number, let's label this as, call this equation number 3, 4, and 5, then 4 minus 3 will get rid of most of these terms. This will go away, this will go away, this also will go away, and then this part and this part will go away, right? Except for the mixing term. So you end up with nothing but 4 beta y sine alpha is equal to 4 zeta beta minus w times sine alpha, right? Which is nothing but y equal to zeta times 1 minus w over beta. So we have one parameter sorted out. Okay, and then if you add equations 3 and 4, I do 3 plus 4, then I get a new equation, which is x prime square plus y square plus beta square minus 2 beta x prime cosine alpha is equal to w square plus beta square minus 2 beta w plus zeta square sine square alpha. And then from equation 5, you get something very similar. You get x prime square plus y square minus 2x prime. Oops. Plus 1 is equal to w square plus 1 minus 2w. Okay. And a few of these terms obviously cancel out. So b squared, beta square cancels. The ones also cancel. And then what you can do is you can subtract these two equations from each other to give you what x is. And I'll just quickly write the result. It's fairly straightforward because all these terms cancel and you end up with just x times some coefficient and the difference between these two terms, right? So it's very simple algebra. You end up with x prime is equal to minus of minus 2w plus 2 beta w minus zeta square sine square alpha divided by 2 times 1 minus beta cosine alpha. Okay. And then from that, you can write x now, which was 1 minus x prime, right? So 1 minus of that, which is nothing but 1 minus zeta square divided by 2 sine square alpha plus 1 minus beta w. All of this divided by 1 minus beta cosine alpha. And that's the second equation. So we have one equation for y and one equation for x. Right, so what I can do is I can substitute both of these equations into this one, as this looks the simplest. And that should give me an equation for w, right? That is actually a long equation. So let me write that down. Okay, so once you substitute basically x and y back into this equation here, and then go through a bunch of algebra, basically, it's not that long. It's a few steps, but I'm skipping it here because it's sort of too long to write out. But I did do it separately and check it. And these equations are popular. You can find them in a few papers also. So it's not that hard. I'll leave some links in the description anyways. So, okay, so what do we have here? We have a quadratic equation in W with three coefficients, A, B, and C, which are given by these big terms here, right? Essentially. All right, so what we need to do now is we've said, okay, given a certain F1, F2, and alpha, right? You can find essentially what the XY, the right contour is, um, and the length of all those lines W's are, right? By solving these three equations. So let's label these equations. I'll say, okay, this one is, let's call this equation 6. Maybe I'll say this is 6a. Right, this one is 6b. Right, and this whole thing is equation 7. And that kind of solves half the problem, right? So we've essentially said that now we know, if you go back up to this plot now we know how to, where these points lie, right? And where, not those points, but what the length of all these lines is, right? For a given y3, for a given f2, f1, and alpha, essentially. We still want to find out what is this contour. So that's the last remaining part. So once we know that, then we're ready to make the lines, right? Okay, so let's do that. Let's go back down. That's also just some geometry and algebra, but it's important to do it. So I'll call that the beam port geometry. Okay. So we have what, right? We have 3 points. Since f1, f2, and alpha are defined, we know exactly where these 3 points lie, right? But we only have 3 points. We don't have a full contour on the left, right? So the question now becomes, okay, what should be the contour that passes through these 3 points, right? So should my beam ports lie on a contour like this? Or should they lie on a contour, like this? That didn't work out well. Like this, or maybe like this, right? We don't know that. And there are actually different solutions to this problem, but the one that I see seems to be the most popular, the one that maybe I've worked with or I recommend is the one where you have a single circle that passes through all 3 points, right? So if you have 3 points, we know that there's always a circle a unique circle that passes through 3 points, right? And that's the circle, that's the contour that we'll use. So we say essentially that, okay, there is some kind of circle. Hopefully that makes a circle. Okay, there we go. It's easier to put points on a circle rather than, okay. So I say, okay, this is my, did I call this F1? I think, yeah. This is F2, and then this is F3, right? And the rest of the points essentially lie on this contour. That's what defines the contour. But we still need to know what exactly the radius of that circle is, right? Where is the center of the circle and where is the radius? We don't know that yet. So to do that, let's draw another figure on this side. So let me say, okay, this is F1 here. And I have F2 somewhere here. I'll only draw F2, I won't draw F3 because it's symmetric. Right, there we go. And then I have this line here. And this is some point, I don't know, O, doesn't matter. And then let's say, okay, my center is somewhere here, right? Or say it's somewhere here. Okay, I'll call this point C, let's say. Which means what? Which means that this length is, let's say, rho naught, just some length. And this length is also rho naught. About this length. Okay. We need to label that. Okay. Which means that, and here let's use sort of normalized coordinates or normalized lengths. So essentially, I'm normalizing all lengths to F1. And if I do that, then this length, which was F1 earlier, is now just equal to 1, right? F1, which now goes to 1, which means that this length here is 1 minus rho naught. 1 minus rho naught. And this length now, which was F2, is beta, right? Which we already defined earlier. Okay. And we obviously have our contour of our circle, which goes like that. And let's say if you pick a random point on there, right, that connects down here. And we'll also draw another line to this point. Okay. One more label, which is this one is alpha. And actually move this down. Call this angle alpha prime. And this angle is P. Okay. All right. Now let's go through some more simple geometry. We want to find out what is rho naught, right? And for that, we can use the law of cosines for this triangle. Okay. And that gives me rho naught square is equal to 1 minus rho naught square plus beta square minus 2 beta 1 minus rho naught cosine alpha. And from that, you can easily find rho naught to be, because this rho naught and this rho naught would cancel, except for the coupling term. So you get rho naught is equal to 1 plus beta square minus 2 beta cosine alpha divided by 2 times 1 minus beta cosine alpha. And that can be rewritten as 1 minus beta square over 2 times 1 minus beta cosine alpha. Okay. All right, so that's nice. So we have the radius of the circle, which means that we know where the center of the circle is, right, on this line F1O. The next thing we need to know is that for a given exit angle, let's say I want to exit finally from my array, right? So I reach here, it goes through some line, and then it exits at some angle, right? So for this element out here, for this element, if I have some exit angle, which is, let's say, theta, right? I want to know what should be the location of this element for a given exit angle theta, okay? And if you recall, we already defined gamma, right? If you go back, where are the definitions? Yeah, here. So we defined this term gamma, right, as sine of psi divided by sine of alpha. Again, psi was the exit angle when you were at this focus, right? Which means that if you're off the focus, now the exit angle is theta, so an alpha became alpha prime, right? So the ratio of that should be the same. So not psi, sorry, gamma was sine psi divided by sine alpha, which is the same thing as the new exit angle or the general exit angle, sine of theta divided by sine of alpha prime, right? So the special case of this is when alpha prime is equal to alpha and theta equal to psi, and that was the definition of gamma, right? So from this, we can say that for a given exit angle theta, alpha prime is sine inverse of sine theta divided by gamma. That's another important equation. Okay, and even this is important, so I'll just put this in brackets. All right. Now we're only left with one equation, one last thing that we need to find, which is this angle, phi. Again, the reason we need to find that I'll tell you, but let's find that first. So that's also fairly simple. We just have to apply now the law of sines for this triangle. Okay, and that gives us exactly what we want. Right, because even this length now is rho naught. So applying the law of sines, you get sine phi divided by 1 minus rho naught is equal to sine alpha prime divided by rho naught, which implies that phi is sine inverse of 1 minus rho naught over rho naught sine alpha. Okay, that's another important equation. Okay, so now what do we have? We have all of these angles and distances and so on. But what we want to find is the location of this point, right, in x and y coordinates. And now that we have all these angles, it's actually fairly straightforward. So if you look at this angle, right, this angle is nothing but phi plus alpha prime, which means that this angle is 180 minus phi plus alpha prime. Phi minus alpha prime, right? Okay, so let me redraw that a little bit in a new page. This copied, I think. So let me write this as vectors now, make it easier. So let's say I call this vector as u, this vector as vector v, and this vector as vector q, right? For some point q of x comma y. Then it's fairly straightforward to see that vector q is nothing but u plus v, right? And u is rho naught comma 0 plus vector v is rho naught cosine of 180 minus phi minus alpha prime, comma rho naught sine of 180 minus phi minus alpha prime, right? Of course, when you're making the vector, you need to take this as the center, right? So that's why I have the 180 minus phi minus alpha prime. Okay. And that essentially gives us x and y. Call it x naught, y naught rather. X naught, y naught. And these are also normalized coordinates. Remember that, because rho naught is normalized, right? So rho naught times 1 minus cosine of alpha prime plus phi, right? And that's just this plus this. And y naught is rho naught sine of alpha prime plus phi. And that basically completes our geometry. Okay. So that is equation number 8. Okay. So we now know how to find the left contour, right? Based on some origin here. We know how to find the right contour as well. Maybe like that. And given an array of elements out here, we know how to find the length of all these lines as well. Right? So I'll put some antennas out here. So this is given by equation 7. This is given by equation 6. And this is given by equation 8. Okay. So the design is essentially that we are given alpha, gamma, f1, or we can choose rather, and beta. Right? Can you really choose beta? That's a separate question. Beta is nothing but f2 over f1, right? Isn't that what beta is? Let me quickly check. Yes, f2 over f1. Is that really arbitrary? So in their original paper by Turner and Rotman, they actually argue that if you choose beta equal to approximately 2 over 2 plus alpha square, then the phase aberration from all those points, the chromatic aberration between the two ideal foci is low, right? And that's sort of, there's not a very rigorous argument for it, but we'll choose beta very close to 1, right? 0.9 or 0.95 or so on, right? Or you can also use this equation if you like. We'll play with those numbers and see what happens. Okay, so you're given these values, you're given all of this, and we want to find these, right? This geometry of this line, and this line, and now we have equations to do that. Okay. So you have some ports basically that connect out here. And the port locations is known from equation 8. But you also have this region out here, right? This region out here and this region out here. And usually what is done is that they place some ports out here and match these ports so that all of the signal that's going to all of these ports doesn't get reflected back and enter the output port. So you don't want this multiple scattering kind of behavior, because that'll corrupt the phase of the outputs, and that introduces side lobes in the radiation pattern. Okay, so there are many ways actually to mitigate this, and quite a bit of research has been done in trying to find out what's the ideal kind of geometry for this shape. So maybe something like that or something like this, right? The different options. When we actually implement it, we'll see that you can pick different options to do that, and we'll set up that as part of the code really. But yes, so that essentially now completes the Rotman lens, right? You have, I mean, what we'll do is we'll set a polynomial that joins this end to this end like this based on some points, right? And ideally you want to make this kind of sharp. You don't want it to be like flat like this. Otherwise you'll get a very strong reflection. If it's something like that, maybe you get some reflection back this way and not much that goes into those pores, right? And that's what we'll try to do. Okay, so you have the final lens design now. Let me erase this, maybe this line. Right, so you have your, these are your beam ports. Then you have a bunch of array ports, I'll call them. That's what they're called usually. Then you have some dummy or matched ports, right? And this side and this side. And for certain applications, you may not need these dummy ports depending on what you're trying to do. So for example, for wireless power transfer or for power harvesting kind of applications, you don't care, right? You don't care about the side lobes. You just want to collect power from the main lobe. If there are some side lobes, that's okay. But for other applications, it's important to kind of suppress them, and we'll see how to do that. And now if you go back and look at, let's say, a standard design of a Rotman lens, it's now easy to identify what's going on. So let's actually take a quick look at one of them. Okay, so you can kind of see here that I have, let me actually copy this onto, oh, that's fine. So you can see on the left, you have these, on the left, you have your beam ports. On the right, you have the array ports. And then you have these lines on the right that have different lengths based on the Ws. And it looks kind of like a lens inside, right? And the reason we can use sort of geometrical optics is because it's like a parallel plate waveguide. And ray tracing is not a bad approximation, basically. And on the top and bottom, you have all these matched ports, right? And now if you look at any Rotman lens, it quickly makes sense what's going on, right? In this case, you on the left and right, you have matched ports. On the top, you have the beam ports. And the bottom, you have the array ports. And you can take even more complicated structures. And I guess here is exactly the figure that we drew earlier. Even large Rotman lenses will kind of make sense now. Okay, so you can go through that and look at different designs. All right, so next what we'll do is, let's go back to our notes. So next what we'll do is I'll stop the discussion of the theory right now, but in the next video, we'll go ahead and implement these equations 6, 7, and 8 in a MATLAB code that generates a 3D model, not a 3D model, but let's say a 2D model of a Rotman lens. We'll import that into HFSS, design a Rotman lens, excite ports, look at the beam steering, and look at the side lobe levels, things like that, and play around with some designs. So hopefully you're excited about that and you enjoyed this video. If you have any comments or if you have any suggestions or if I made any mistakes, please leave them in the comments below. If not, I'll see you in the next one. Thank you.